Right now, somewhere online, a headline is telling you Vera Rubin's first images just stopped the world 6 minutes ago, as if a telescope in Chile just switched on and froze the entire planet in place. Here's the truth. Nobody wants to slow down and tell you. Those first images are real. They really did stop people in their tracks, scientists and casual viewers alike. And the reaction genuinely was that dramatic. What actually happened wasn't a sudden event from a few minutes ago. It was the culmination of more than 2 decades of construction, testing, and engineering released to the public on a single morning in June 2025. And what's happened in the year since has been even bigger than that first release. Because the Vera C. Rubin Observatory isn't just another telescope, it's arguably the most ambitious astronomical instrument ever built for a single purpose, filming the entire visible universe as a continuous 10-year movie, cataloging changes that no human being has ever had the tools to track at this scale before. And the first images it released didn't just look impressive, they came packaged with numbers so large that professional astronomers, people who see extraordinary data for a living, were visibly stunned in real time. This is the real story of the Vera C. Rubin Observatory. The astronomer it's named after the morning its first images actually did stop the scientific world, and what's happened since as the most powerful astronomical survey in history has finally, fully turned on. Start with the person the observatory is named after, because her story is inseparable from what this telescope was built to do. Vera Rubin was an American astronomer who, in the 1970s, working alongside colleague Kent Ford, made one of the most consequential discoveries in modern astrophysics. While measuring how fast stars orbited within spiral galaxies, Rubin found something that shouldn't have been possible under the physics known at the time. Stars at the outer edges of galaxies were orbiting just as fast as stars closer to the center, when standard gravity, based purely on the visible mass of stars and gas, predicted they should be moving much slower. The only explanation that fit the data was that galaxies contain vastly more mass than what's actually visible, matter that doesn't emit or reflect light at all. Rubin's careful, painstaking measurements became some of the strongest observational evidence ever gathered for what we now call dark matter, a substance that appears to make up roughly a quarter of everything in the universe, and that remains, to this day, one of the largest unsolved mysteries in all of physics. Naming a telescope specifically built to hunt for more clues about dark matter and its equally mysterious counterpart, dark energy, after the woman whose work first proved something invisible was out there, was about as fitting a tribute as astronomy has ever produced. The observatory itself sits atop Cerro Pachon, a mountain in central Chile, chosen specifically for its dark skies and dry, stable air, ideal conditions for astronomical observation. It houses an 8.4-meter telescope paired with the largest digital camera ever built for astronomy, a 3.2 gigapixel instrument roughly the size of a small car, capable of capturing images so large that displaying just one of them at full resolution would require hundreds of ultra-high-definition television screens. The entire project, jointly funded by the U.S. National Science Foundation and the Department of Energy's Office of Science, cost roughly $810 million and took more than 2 decades to move from initial concept to a fully operational instrument, involving more than 2,000 scientists and engineers across research institutions worldwide. On June 23, 2025, after that entire multi-decade journey, the Rubin Observatory team gathered in Washington, D.C. and released the telescope's first public images, drawn from just over 10 hours of test observations. What came out of that single day of data collection was, by any honest measure, staggering. One image, built by combining 658 separate exposures, captured over roughly 7 hours, revealed the Trifid and Lagoon nebulae, vast stellar nurseries several 1,000 light-years from Earth, in a level of detail that made previously faint, barely visible structures of gas and dust suddenly crisp and vivid, glowing in vibrant pinks and oranges that had simply never been resolved this clearly before. A second release, nicknamed the Cosmic Treasure Chest, showed something even harder to fully process. Roughly 10 million individual galaxies, visible in a single wide-field composite, representing barely 0.05% of the roughly 20 billion galaxies the observatory expects to observe over its full 10-year mission. Astronomers accustomed to studying galaxies one at a time, or in small, carefully selected clusters, were suddenly looking at 10 million of them appearing casually in a single afternoon's test run. But the number that actually generated the most immediate, visceral reaction inside the scientific community wasn't a galaxy count, it was asteroids. In that same roughly 10-hour test observation window, Rubin's camera detected 2,104 previously unknown asteroids in our own solar system, including 7 near-Earth asteroids, none of which pose any danger, but all of which had simply never been cataloged by any telescope on Earth before that day. To put that number in context, every other ground and space-based observatory on the planet combined typically discovers around 20,000 new asteroids in an entire year. Rubin found over a tenth of that annual global total in less than half a day, during what was technically still just a testing phase before the telescope had even begun. Its real primary survey. That single statistic is a large part of why "stopped the world" isn't pure exaggeration when applied to that specific morning. Researchers who had spent entire careers painstakingly tracking down individual asteroids one at a time were watching a single machine casually outproduce years of dedicated searching in a matter of hours. Here's why that capability matters far beyond simple bragging rights. Rubin Observatory's mirror design, its extraordinarily sensitive camera, and the sheer speed at which it can sweep across the sky were all specifically engineered to catch faint, moving objects that slower or narrower surveys would simply miss entirely. Officials at the observatory have stated plainly that within just the first 2 years of its full survey, Rubin alone is expected to discover millions of new asteroids, a number that dwarfs the entire cumulative asteroid catalog humanity had built up across every other observatory combined before Rubin ever came online. That capability isn't just useful for cataloging space rocks out of scientific curiosity. It's directly tied to planetary defense, the ongoing effort to identify any object on a potential collision course with Earth early enough to actually do something about it, and Rubin's ability to catch faint, fast-moving objects makes it, by design, the most effective asteroid hunting instrument ever built. The momentum didn't stop after that first public reveal, either. Rubin's path to that June 2025 milestone had actually begun months earlier, in October 2024, with an initial testing campaign using a smaller commissioning camera to verify the observatory's hardware and software worked correctly end-to-end. The full 3.2 gigapixel LSST camera, the instrument responsible for those first jaw-dropping images, was installed in April 2025, just 2 months before the public reveal. After that reveal, the observatory formally transitioned into operations on October 25, 2025, beginning a careful, methodical optimization phase, designed to fine-tune the system before committing to its full decade-long survey. Even during that comparatively cautious testing period, the discoveries kept mounting. In just 6 weeks of this optimization phase observing, Rubin detected more than 11,000 previously unknown asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects drifting in the distant icy reaches beyond Neptune's orbit. Then, on February 24, 2026, the observatory hit another milestone entirely: the launch of its real-time Discovery Alert System, a pipeline designed to flag anything in the sky that had visibly moved, brightened, faded, or otherwise changed since the telescope's last look at that same patch of sky. On its very first night of operation, that alert system captured 800,000 transient alerts, a single night's worth of automatically flagged cosmic changes that would have taken earlier generations of astronomers years of manual comparison to identify by hand. Finally, on June 30th, 2026, after that entire staged rollout, the Rubin Observatory officially began its primary mission, the Legacy Survey of Space and Time, or LSST, a full 10-year commitment to photographing the entire visible southern sky, over and over hundreds of times across the coming decade. NSF Noir Lab, the Department of Energy's SLAC National Accelerator Laboratory, and Fermilab jointly announced the start of full operations, with officials describing the effort. In suitably dramatic terms, one NSF representative calling it the start of filming the greatest cosmic movie ever made. Under full operations, the observatory is expected to generate roughly 7 million automated alerts every single night, an almost incomprehensible torrent of real-time data, flagging supernovae, pulsating stars, asteroids, comets, and astronomers' hope. Entirely new categories of cosmic phenomena nobody has ever directly observed before, all streamed out continuously to a global network of researchers and automated follow-up telescopes standing ready to respond. One of the survey's central scientific goals sits directly at the intersection of Rubin's own namesake discovery and one of the biggest open questions in modern cosmology: testing, with unprecedented precision, whether dark energy, the mysterious force behind the accelerating expansion of the universe, is a fixed, unchanging constant, or whether it actually evolves over cosmic time. Answering that question requires exactly the kind of enormous, consistent, repeated dataset Rubin is uniquely built to generate, tracking billions of galaxies across a full decade to detect subtle patterns no shorter survey could ever hope to catch. There's also a genuinely democratizing element to how Rubin's data is being shared that sets it apart from many previous major astronomical projects. The final 10-year dataset is expected to contain billions of individual objects and trillions of separate measurements, all accessible through publicly released data updates, opening up serious astronomical research to students, amateur astronomers, and curious members of the public in a way that's rarely been possible with instruments of this scale before. The observatory team has even built an interactive sonification tool available through their Sky Viewer app, letting anyone translate the colors and brightness of Rubin's ultra-detailed cosmic imagery into an immersive, ever-shifting soundscape, giving people without any technical astronomy background a genuinely new way to experience what the telescope is actually seeing. There's a particularly striking coincidence worth mentioning too, one that speaks directly to exactly the kind of discovery Rubin was built to make possible. Just days after that first public image release in June 2025, astronomers, using a separate NASA-funded survey telescope in Chile, discovered 3I Atlas, only the third confirmed interstellar object ever detected passing through our solar system. Rubin itself wasn't responsible for that particular discovery, but observatory. Officials have been direct about what its own sky scanning capability means for exactly this kind of object going forward. Rubin is expected to become the most effective observatory in history at spotting interstellar visitors, potentially transforming what has, up until now, been an exceedingly rare, once every few years event into something researchers can expect to encounter far more regularly as the full 10-year survey unfolds. It's worth spending a little more time on Vera Rubin herself, because her career adds real weight to why this specific telescope carries her name, rather than simply being named for a funding agency or a geographic location, which is how many major observatories get their names. Rubin earned her graduate degree in physics at Georgetown University in 1954, at a time when the field remained overwhelmingly closed to women, and she spent much of her early career facing direct, documented resistance simply to access the observing time and academic standing her work required. Despite that resistance, her measurements of galaxy rotation, painstaking, repeated, and methodologically careful, became so difficult to dispute that they helped shift dark matter from a fringe theoretical curiosity into one of the central problems in all of modern physics. She never received a Nobel Prize for that work, a fact many in the scientific community have long considered one of the more glaring omissions in the prize's history. But by the time this observatory was being planned, naming it after her had become something close to an obvious, overdue choice. Recognition that arrived posthumously but permanently, etched into the identity of the exact kind of instrument her own work had helped make necessary. It's also worth understanding just how much raw engineering had to come together correctly for that first image release to happen at all, because the numbers involved are almost as remarkable as the images themselves. The LSST camera weighs roughly 3,000 kilograms, works with an 8.4 meter primary mirror polished to a precision measured in nanometers, and captures light across 6 different optical filters to build up a detailed picture of each object's true color and composition. Each individual exposure lasts only 30 seconds, deliberately brief, so the telescope can sweep across enormous areas of sky quickly enough to catch objects that move, brighten, or fade within a single night, rather than lingering on any one target the way many traditional telescopes do. That combination of speed, sensitivity, and sheer resolution is exactly what let a single 10-hour test run outproduce years of dedicated asteroid hunting from earlier instruments, and it's exactly why astronomers who understood the underlying engineering were bracing for something impressive well before the first images were actually unveiled. What still managed to catch even those well-prepared experts off guard wasn't that Rubin worked. It was watching, in real time, just how far past every reasonable expectation the results actually landed. The reaction inside the room in Washington, D.C. on the day of that first reveal is also worth understanding in more detail, because "stopped the world" genuinely does describe something that happened, even if it wasn't literal. Astronomers who had spent their entire careers studying narrow slices of the sky, one galaxy cluster, one nebula, one small patch of stars at a time, were confronted in a single presentation with a dataset that dwarfed years of their own individual research. Output. Stephen Ritz, a distinguished professor of physics at UC Santa Cruz who led the team producing the imagery for that first release, had spent years anticipating what the data would eventually look like, having joined the project as its construction project scientist back in 2022. Even with that years-long anticipation, watching the actual results appear, 10 million galaxies rendered in a single composite frame, thousands of asteroids identified in a single test run, was something colleagues across the field described as viscerally different from simply reading the specifications on paper beforehand. That gap between knowing intellectually what a telescope like this should theoretically be capable of and actually watching it deliver those results in real time is precisely where the genuine shock in the room came from. The public reaction outside that room mirrored it almost immediately. Within hours of the release, video footage built from over 1,100 of Rubin's images began circulating widely online, opening with a detailed, intimate view of 2 individual galaxies before dramatically zooming outward to reveal the full 10 million galaxy field hiding behind them. That kind of visual pacing, starting small and personal before suddenly revealing overwhelming scale, is exactly the sort of moment that translates naturally into the kind of shareable, viral astronomy content that genuinely does stop people mid-scroll, independent of any exaggerated headline wrapped around it afterward. In this particular case, the underlying substance actually held up. The universe Rubin revealed that day really was that vast, and the telescope really had caught that much of it in barely 10 hours of test observations, no embellishment required. It's also worth taking a moment to appreciate exactly how unusual it is for a scientific instrument this significant to also be this immediately, viscerally understandable to a general audience. Plenty of major astrophysics projects produce results that are genuinely groundbreaking but require a physics background to fully appreciate subtle shifts in a graph, statistical significance levels, incremental refinements to an existing model. Rubin's first images sidestepped that barrier almost entirely. You didn't need to understand galaxy rotation curves or dark matter physics to feel something looking at 10 million galaxies rendered in a single frame, or to grasp what it meant that a machine found more asteroids in 10 hours than most of humanity's combined observational effort finds in weeks. That accessibility is part of why the reaction spread so far beyond the astronomy community itself, reaching casual news audiences and social media feeds that rarely engage with space research at all, and it's exactly the kind of moment mission planners hope for but can rarely engineer on purpose. In this case, the sheer scale of what the telescope was built to do turned out to be its own best advertisement. No exaggeration necessary to make people stop and pay attention. There's also a genuinely useful contrast worth drawing between Rubin's approach and how most previous major telescopes have operated throughout the history of astronomy. Instruments like Hubble or the James Webb Space Telescope excel at pointing intensely at a single target, gathering enormous depth and detail on one specific galaxy, nebula, or planet at a time, often over hours or days of dedicated observing time. Rubin was built to do almost the opposite. Rather than staring deeply at one thing, it sweeps broadly across everything, trading some depth on any single target for breadth across the entire visible sky, revisited over and over across a full decade. Neither approach replaces the other, and astronomers have been clear that Rubin's real power comes specifically from working alongside instruments like Webb, flagging interesting or rapidly changing objects across its nightly scans, that other, more specialized. Telescopes can then follow up on and study in far greater depth. That division of labor, one telescope covering everything broadly and continuously, others diving deep into whatever it flags as interesting, is quickly becoming the model much of modern astronomy is organizing itself around. And Rubin's first images were really the opening proof that the broad half of that partnership was finally ready to deliver at the scale everyone had spent 2 decades promising it eventually would. There's one more number worth sitting with before closing this out, because it captures the sheer scale of what's still ahead better than almost anything else in this story. 10 million galaxies sounds like an almost unimaginable haul for 10 hours of test observation, and it is. But Rubin's own team has been explicit that even that figure represents only about 0.05% of the roughly 20 billion galaxies the full 10-year survey expects to eventually catalog. Multiply that first morning's results out across the 9 years still remaining. And the first images that already stopped a room full of astronomers in their tracks start to look less. First frame of a much longer film, one still being shot, one clear night at a time, high above the Chilean Andes. So here's the real story, once you strip away the fake urgency and let the actual timeline stand on its own. Vera Rubin's first images really did stop a room full of professional astronomers and a much larger online audience in their tracks. But that moment happened in June 2025, not 6 minutes ago. And it was only ever meant to be a preview, a single brief glimpse of what more than 2 decades of careful engineering had finally made possible. In the years since, that preview has grown into something far larger. A fully operational decade-long survey now streaming millions of alerts every single night, already responsible for tens of thousands of new solar system discoveries before its primary mission had even officially begun. The world didn't just stop for one morning in Washington. It's still, right now, tonight, over Cerro Pachon, quietly filming the single most detailed movie of the universe humanity has ever attempted to make, one image at a time for the next 9 years still to come.